Heat transfer analysis of a Dodge Ram1500 exhaust system for a custom carbon fiber exhaust tip. It is desired to create a carbon fiber exhaust tip to replace the existing stainless steel tip. The carbon fiber tip will be created by taking a stainless steel tube and wrapping it in a carbon epoxy composite. The epoxy chosen for this part can reach a temperature of 370 degrees Fahrenheit and maintain the required material properties. The purpose of this analysis is to create a model that predicts the surface temperature of the exhaust tip to determine if this epoxy will burn. A SolidWorks model was created to approximate values of the exhaust at the exit of the system, giving a temperature range between 440 and 480 Kelvin. Because this temperature range contains values close to the max temperature of the epoxy, it was decided to pursue this project. The SolidWorks model was also used as a visual representation of the different modes of heat transfer. As seen in the animation, exhaust enters the system at a temperature of TMI, then flows to the split right after the muffler, and exits the system at TMO 1 and 2. In order to solve this system, each section of the pipe was separated, and TMO-M was used as the average mean exit temperature for section 1 and the average mean input temperature for section 2 and 3. Radiation was neglected due to the air velocity. For this particular engine, a horsepower curve is given by the manufacturer. This curve can be used to find a correlation between RPM and horsepower. The amount of power entering the exhaust can then be found and used as a storage term in our system.
We wanted to make this model as easy as possible for the user, so 3 readily available user inputs were selected: RPMs, ambient temperature, and truck velocity. Using correlations and measured temperatures, we were able to break the exhaust system into 3 internal and external convection loss terms under the assumption of constant T infinity, along with energy stored sections to account for the exhaust in both pipes. The TMO is the tip temperature of the exhaust that we're looking for. The energy storage terms were broken into 3 sections, the first being before the section before the TMO-M, and the other 2 being the exhaust pipes behind the passenger and driver. For our tote, we found the external convection coefficient iterating the properties of air, and the internal convection coefficient was found iterating properties of carbon dioxide, because CO2 is the most common gas in the truck exhaust. To find the convection coefficient, we need the air velocity under the truck. To find the velocity underneath the truck, we placed a wind speed gauge underneath the tailgate and drove at 5 different truck speeds, 10, 20, 30, 40, and 50 miles per hour, and recorded the average wind speed underneath the truck at those speeds in order to create the correlation. The correlation was fairly linear, giving us confidence to use the approximated wind speeds. The reason why the wind speed is 0 at first is because the wind speed gauge didn't read any values beneath around 9 miles per hour. The same wind speed gauge was used to measure the exit speed of the exhaust at both exits in order to find the correlation between RPMs and exhaust mass flow rate for each exhaust pipe. These 2 figures show the correlations of the passenger and driver side exhaust pipe mass flow rates at any given RPM. 2 modes of heat transfer were found to be negligible: the conduction resistance and the energy generated in the catalytic converter. The total resistance, meaning convection plus conduction, was 12.27, and the resistance with just convection was 12.12, resulting in a difference in total heat transfer of less than 1%. Therefore, the thin-walled approximation was used. We were expecting a rise in temperature across the catalytic converter due to a combustion reaction. However, there was a temperature decrease across the cat due to the increased amount of convection across the cat.
The calculated and measured values were compared at 2 different RPMs of 1500 and 2600. The percent air can then be calculated, which ranges from 30 to 50%. It is also noticed that the model does predict the exhaust temperature closely, but not the surface temperature of the tip.
One way to improve the accuracy of the model would be to measure more accurate velocities across the exhaust pipes underneath the truck. The airspeed increased and decreased dramatically going up and down hills, but our correlation was based on a level road. Also, we only found the airspeed at the rear end of the truck. So due to the turbulent flow underneath the truck, the more locations we could have measured the wind speed, the more accurate the model would have been.
Another reason the model closely predicts exhaust temperatures but not the surface temperature of the tip is attributed to the sudden change in diameter as the flow enters the tip. As shown in the animation, the flow enters the tip and begins to expand, but the expansion is almost unnoticeable by the time the fluid exits the system. This situation would cause very little energy transfer to the walls and therefore the surface. Because of this fact, it is believed that the model would be accurate if this phenomenon was taken into account.